Now, let's solve some question. Let's take up some questions. This is our first question. See what it is given. It is given 5t. Means STM is given e to the power minus 3t 0 0 e to the power minus 2t. This is my STM. This is my STM, and it is asked that find phi square t. So see, it is a direct question on a property of STM, where we know that phi square t will be equal to phi 2t. Phi square t will be equal to phi 2t. We have seen in the property of STM where I wrote that phi to the power kt will be equal to phi kt. So it's a direct question on the property of STM. So let's see what will be the option. 2 2 2. So this will be the option. E to the power minus 60 0 0 e to the power minus 4t. Okay, easy. Now let's see another question. Whose? So what it is given here? It is given STM whose state equation is this. It is saying that we are having a state equation. We are having a state equation x dot t is equal to axt, and STM is given. This is the STM. This is the phi t. This is phi t. Now we are asked to find matrix A. We are asked to find matrix A. So what we know is that phi t is equal to inverse Laplace transform of Si minus A. See, if we will go by this method, so it will a lot of time will be required to solve this question. In this, what we have to do, we have to pick randomly each matrices given. Then we have to do this whole calculation Si minus A inverse, and then its inverse Laplace transform. But suppose if you know the property of it, which I have told you, then this question can be solved within half a minute. See what I told you? I told you that we had a property d phi t by dt at t is equal to 0 is equal to matrix A. This property I told you, and I also told you that this is a very important property. This property, the last one, this one, I told you that this is also important, and this is also very important. It will help you in solving a question within minutes, and this will be the deciding factor between you and your competitor. Here, if you remember the property, then you will solve this question within a minute, and if you doesn't, then it will take you around 4 to 5 minutes to solve this question, and this 3 to 4 minute gap will be a deciding factor between selection and rejection. So now see, if we will go by this property, then we will take a differentiation of this, and at t is equal to 0, what we will get? We will get something like this. If we differentiate it, it will become minus 2 e to the power minus 2t, and this will become minus 2 e to the power minus 2t plus 3 e to the power minus 3t. This 0, this minus 3 e to the power minus 3t. Now if we let me write it here. If I put t is equal to 0, then what we will get? We will get here -2. Let's check it from the option. -2, -2. Here we will get -3. Here is 0 only. Here we will get -2 plus 3 means 1. Means -2, 1, 0, -3. This will be the right answer. So I think that now you are comfortable with all this questions, and by knowing the property, you can solve all these questions within 1 or 2 steps only. So let's now see the next topic. Now see, in type 5, we had all these things. So what all we have covered? We have covered solution of state variable. We have covered we have covered solution of state variable. We have covered solution of state variable. We have covered this STM part. Now we will look into solution of transfer function, and before that we will look into the calculation or solution of output. It is not output equation, it will be calculation of output. It will be the calculation of output. So let's see. Solution of output. So we know that the state model has two equations. First is the state equation, and second one is the output equation. So let me write it again. State variable input. This is the state equation, and we also has output equation. It is this. It is this. Okay, fine. In our previous session, we saw that how we can find solution of a state variable. How we can find solution of state variable, and there what we got? We got excess. Let me write it here. Solution of state variable. Solution of state variable. What we got? Let me take it little lower. We got x of s, si minus a inverse x of 0 minus si minus a inverse b u of s. This is the solution of state variable. This we calculated. Okay. Now see, we have to find the solution of output. We have to find solution of output. So now, if we will take Laplace of output equation, if we will take Laplace of output equation, I can write it here. If we can take Laplace of output equation, Laplace of output equation. So what we will get? We will get something like this. Y of s c x of s d u of s. Now see, now what we will do, we will put value of x of s. We will put value of x of s here. We will put value of x of s, that is solution of state variable x of s. We will put solution of state variable x of s here. So let's see what we will get. We will get something like this: y of s, let it be c. We will take the whole term inside, si minus a inverse 0 minus si minus a. This is also matrix. See, don't let me write it again. This is a matrix. Many times the brackets which I put may be different, but please don't get confused. Okay, B and US. So this plus we can write plus D US. Now let expand it. If we will expand it, so let's see what we will get here. Yes, we will get this si minus a inverse 0 minus, okay, plus c si minus a inverse b plus d, take it in full bracket, u of s, u of s. This we will get. So this is the solution of output, or this is the calculation of output. It is divided into, let's divide it into two parts. Let's call it as A, and let's call it as B. Now students, see, from here we are going to discuss a lot of conceptual things. Most of you must be having misconception about it also. So from here, try to listen it very carefully. We will take number of cases. We will discuss number of conceptual things which will be very important for your interview, ESE objective, as well as for GATE exam. So let's see. Suppose let's discuss case 1. Let's discuss case 1. In case 1, suppose we take initial condition at 0. Let initial condition is 0. Let initial condition is 0, and input is applied, and input is applied. Then see what we will get. What will be our ys? What will be our ys? Ys will be matrix C, then state transition matrix, D and US. This YS is known as zero state response. This is known as zero state response. When our initial conditions are zero, then output equation is known as zero state response. When initial conditions are zero and input is applied, then we will get ys is equal to this, and this ys, that is output, is known as the zero state response, is known as the zero state response. Now suppose let's take case 2. Input is 0, input is 0, initial condition is not equal to 0. Then what will be our output? Our output will be this. If u is, in the first case we took initial condition 0, now we are taking input 0, so we will get this one, matrix C, state transition matrix, and here we will get our initial condition. So this response is known as zero input response. This response is known as zero input response. Very important. These things are very important. So see it carefully. So when we took initial condition 0, we got zero state response. When we took input 0, we got zero input response. So we can say that IS is a combination of zero input response plus zero state response. Can we say it like this? So output is a combination of zero input response and zero state response. Here, zero input response is also known as natural response. Zero input response is also known as natural response. These all terms are asked you in ESE pre-exams. So be familiar with these terms. Zero input response is also known as natural response. Zero state response is also known as forced response. Is also known as forced response. Is also known as forced response. Okay, I think it is clear. Yes. Now coming to another case. So what we got as a ys can be written as C Si minus A inverse initial conditions plus C Si minus A inverse B plus D U of S. Now see, Si minus A inverse can also be written as adjoint of Si minus A by mod of Si minus A. We can write it as this. We can write Si minus A inverse as adjoint of Si minus A by mod of Si minus A. It's a simple matrix property. So suppose now put it into this equation. Now put it into this equation. What we will get? We will get ys matrix C adjoint Si minus A initial conditions mod of Si minus A. Then here we will get matrix C. Here we will write adjoint of Si minus A B D. Here we will get U of S divided by mod of Si minus A. Okay. Till now it is okay. So now if we will take a US this side, suppose we take US this side, what we will get? Y of S by U of S, output by input. What it is called? Y of S by U of S. No, previous. Yes, no. Forget it. Yes, Y of S is this. Y of S is this. So we have got in the denominator mod of Si minus A. Here also mod of Si minus A. Okay, fine. So we know that denominator of ys, denominator of ys denotes what it denotes. Denominator of ys denotes characteristic equation. Denominator of ys denotes characteristic equation. So can we say it like this, that characteristic equation is equal to mod of Si minus A. What we will get here? Eigenvalues. We will get eigenvalues. And from characteristic equations, what we get? We get poles of closed loop transfer function. Are you getting it? Very important conclusion is written here. See, in denominator we are getting mod of Si minus A, and denominator of ys denotes characteristic equation. So characteristic equation denotes poles of closed loop transfer function, and in matrices you would have learned that mod of Si minus A also represents eigenvalues. So eigenvalues are the poles of closed loop transfer function. So eigenvalues are poles of closed loop transfer function. Now suppose if we have the characteristic equation, then see what all can we find it from here. We can apply Routh-Hurwitz criteria. We can apply Routh-Hurwitz criteria from here. We can talk about stability of system. We can talk about stability of system. we can define theta, omega n, omega d, means we can calculate all the parameters of time domain analysis. We can calculate all parameters of frequency domain analysis. That is, from characteristic equation, what all we can find and what all we had found in our last chapters, that all can be found out from here. So you can imagine that what type of questions can be asked from you. Suppose they will just give you a matrix A. They will just give you a matrix A, B, C, D, and they can simply ask you anything. They can ask you to find out a number of poles. Then they can ask you to find out number of poles on right hand side of S plane. They can ask you to determine stability, and they can ask you all the parameters of time domain analysis as well as frequency domain analysis. Are you getting it? So just from a single matrix, we can calculate anything, and for that we have to find out eigenvalues, that is mod of Si minus A. I hope this is clear to you. I hope this is clear to you. Now, coming to next point, that is calculation of transfer function. Very important discussion. Just keep on listening my words. Many things are hidden inside the words. Just feel it. Suppose we have a CISO system, that is single input, single output, and suppose we have taken initial condition 0. Initial condition 0, that is we have taken 0 state response, where we have initial condition 0 and input is not 0. So in this case, we have seen earlier that what will be our YS? What will be our YS? Just keep on listening these things. What will be our YS? YS will be C matrix Si minus A inverse B plus D and US. Bring in US this side, Y of S by U of S. What we will get? We will get C matrix Si minus A inverse B plus D. Fine. See, YS by US, output of system by input of system. Can I call it as transfer function? Can I call it as transfer function? So, this is the formula by which you can find out transfer function in case of state space. C matrix, Si minus A inverse matrix, B matrix plus D matrix. Don't ignore D matrix. What happens is that for most part of the questions we take D as 0. So sometimes the examiner does a trick. He puts D in the question, and as we have a habit of ignoring D, we ignore here also, and then we will get a wrong answer. So be careful while calculating the transfer function. So see, from here we got the transfer function. So in the previous case, we saw that how we can find the characteristic equation. In this, we saw that how we can find the characteristic equation, and then we can calculate everything. From here, we saw that how we can calculate transfer function. And now if we have the transfer function, then we have everything. We can analyze each and everything which we have analyzed in previous chapters also. Now see, they give a question. They give a question that calculate steady state error. They gives a question that calculate steady state error, steady state error, steady state error, steady state error. In this, what they will give you? They will give you a matrix. They will give you a matrix. Suppose it is A, B, C, D. They will give you matrix B also. C also. And suppose D also. Take D also something. X, Y. And they will give you a input, a type of input which is applied. Maybe UT, RT, something like this. So can you calculate it? Yes, we can easily calculate it. From this all, I will first find a transfer function, and then I will bring it into this will be the closed loop transfer function. This will be closed loop transfer function. I will bring it into open loop transfer function. I have shown you how we can convert closed loop transfer function to open loop transfer function in my previous lectures. You can refer those, and then we can easily find steady state error based on all these inputs. Fine. But here you can see that two important conditions which I have taken is that system must be CISO, single input, single output, and the initial conditions should be zero. Initial conditions should be zero. Now let's play here. Let's take different combinations which we can take here, and let's see what will happen with transfer function, whether we are able to calculate it, whether we are not able to calculate it, whether it is defined, whether it is not defined, whether it exists, whether it doesn't exist. Very interesting part. Just keep listening to me. Now suppose what I does is that let's take case 1. In case 1, I will take, suppose we have a MIMO system. We have a MIMO system. First condition is we are having a MIMO system, and again we are taking zero state response. That is the initial condition is 0. Initial condition is 0. Then see what we will have. Again write y of s. We will get this Si minus A inverse B plus D. But now we are having a MIMO system. So there will be multiple inputs. There will be multiple inputs. And as there will be multiple inputs, there will also be multiple outputs. We will write it like this. There will be multiple outputs. So now see how many combinations here we will get. We will get something like this. Suppose I assume it as A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, P, Q, R, S, no, S will come, W, X, Y, Z, W, X, Y, Z, Y will come, L, M, that combination will not be there. Suppose anything, uh, let us consider it as uh, w. It will be function of s, it will be function of s, and here we will get u1s. Let this is a function of x. The second part we will get it like this, and this. Now what will be y2s? What will be y2s? What will be y2s? Z of s u2s. So see, here we are getting how many combinations we can get here. We can get here many combinations, like we can get one is y1 by u1 if we take u2 0. Okay, we will have y1 by u2 if we take u1 0. We will have y2 by u1 if we take u2 0, and y2 by u2 if we take u1 0. So we are getting four combinations of inputs and outputs. We are getting four combinations of inputs and outputs. Can I call it a, can I call this a transfer function? 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 No. These all are not transfer function, because we know transfer function is overall output by overall inputs. But here we are not getting overall output by overall input. Here we are getting some ratios at some conditions. Here we are getting some ratios at some conditions. So we cannot say that this is our transfer function, though it may look like a transfer function, but it is not a transfer function. So what we can conclude here, for MIMO system, transfer function is not defined. For MIMO system, transfer function is not defined. For MIMO system, transfer function is not defined. It is not that transfer function doesn't exist. Transfer function is existing in another form, like y1 by u1. It's a also kind of transfer function. Output by input we are getting. One output, one input. But it's not overall transfer function. But it is not overall transfer function. So we can, second statement maybe, transfer function exists. Transfer function exists for a MIMO system, but it is not overall transfer function of a system. It is form of, it is in form of some ratio of input and output. Very important conclusion I am giving you. Very important. You will get such questions in objective, in ESE pre-exam. Such statements are very famous. They like it. They like such type of statements, and we do silly mistakes because our concept is not up to the mark. And in interview also you will be asked same type of questions. For some nice interview, if you appear for BRC ISRO, for there, because there only you get to face interesting and challenging interview questions. So what I told you that so let's come back. Here I told you that system was CISO and we had zero state response. Means initial condition was zero. So and we defined transfer function. Here I am telling you that our system is MIMO. Here another point to note is that here also we are having zero state response. That is initial conditions are zero. But as we are taking MIMO system, so our transfer function is not defined. So here I can give you another important statement that it is not necessary that if you have zero state response, then you will always get the transfer function. It is not necessary. It is necessary for system to be CISO. Then only you can think of getting transfer function. And I am coming to this part that if we have a CISO system and we don't have zero state response, then what will happen? But by the time you just keep in mind that system to be is CISO or system is MIMO is more important as compared to system is having initial condition zero or not. That is, if system is MIMO, there is no chance of getting transfer function even if initial conditions are zero. So I can write it like this. If a system is a MIMO, then transfer function is not defined even for a system having zero state response, that is initial conditions are zero. So I can say that CISO MIMO criteria is more important. CISO MIMO criteria is more important than this zero state response criteria. Zero state response criteria. Very important discussion. Very important discussions. Very important conclusions. Now see. Now take another interesting case. Now take another interesting case. Let's call it as case 2. Suppose we are having CISO system and we are not having zero state response. We are not having zero state response. No. Let me write it like this. That is, initial condition is not equal to 0. Initial condition is not equal to 0. Then see what will be our output. Our output will be C matrix Si minus A inverse x of 0 initial condition plus C matrix Si minus A inverse B plus D U of S. As initial condition is not 0, so we will get this condition, and most importantly we are having CISO system. Okay, now see if anyone asks you that can you find transfer function in this case, can you find a transfer function in this case, then if your concept is weak, then you will say that no, we cannot find transfer function in this case because initial conditions are not 0, which we always study in our statements, that transfer function is Laplace transform of output to input with initial condition 0. See, initial condition is 0 or not 0 is not so important. System has to be CISO. then only transfer function can be defined. Now, coming to your confusion, that if we are having initial conditions, if we are having initial conditions, then how can we calculate a transfer function? So let's see. I will guide you. In this case, if we suppose assume, if we assume initial condition to be 0, if we assume initial condition to be 0, then what we will get? We will get this. See, now US, if I want to bring, if I want to bring US this side, see, our overall output by overall input, is this our transfer function? Yes. Is this our transfer function? Yes. Is this is only our transfer function? How we are getting it? We are getting it by assuming that initial condition is 0. We are getting it by assuming that initial condition is 0. Means we have CISO system, initial condition is not 0. We are getting output like this. If someone asks you that can you find the transfer function of it, you will say it, yes, I can find the transfer function of it, but for that I will assume initial condition to be 0. Okay. Now second question, can you find a output from this transfer function? Can you find output from this transfer function? You will say that yes, I will bring a US this side and then I will take inverse Laplace transform and I will find YT, and that will be my output. So this statement is wrong. You cannot find output from this transfer function. Why? Here also we cannot say that this is the overall transfer function. Suppose this is Y1. Why it is not our overall transfer function? Because here we have assumed initial condition to be 0. Initial condition was not 0 initially. Initial condition was not 0, but just for the sake of finding transfer function, we assumed initial condition 0. Then we found this transfer function. But if we want to find output, then the equation of output is this. Equation of output is this. Equation of output is this. And here we are having initial condition. So here while finding output, we have to consider initial condition. Here we cannot say that initial conditions were given was not 0, but just for the sake of calculating ys, I assumed initial condition 0. It will be wrong. It will be wrong. Your answer, you will get wrong answer. Here just for the sake of calculating transfer function, we assume 0 because I just wanted to tell you that initial condition being 0 is not the only important criteria for a transfer function. Even if initial conditions are not 0, then also we calculate transfer function by assuming it's 0. Important criteria was this CISO MIMO. If MIMO is there, there is no chance of calculating transfer function even if we have a 0 initial condition or not 0 initial condition. But for CISO system, if initial condition is not 0, then we can calculate transfer function by assuming it's 0, but we cannot calculate output from it because expression of output is this, where we have to assume initial condition not 0. So what we can write it here, that in case of CISO and initial condition not 0, we can calculate transfer function by assuming initial condition is equal to 0, or by assuming, let me write it like this only, otherwise you will get confused. Initial condition is equal to 0, but from this transfer function we cannot calculate output. We cannot calculate output because for output we have to assume initial condition. So very important, very important. This points are these points are very important. These points are very important. So in a nutshell, if I see what I have told you, first I took CISO and I took initial condition 0. There we got transfer function easily, and from this transfer function we can get output also. Then we saw memo system and initial condition was 0. Here I told you that transfer function is not defined, and and if transfer function is defined nahi hai, then there is no chance of getting y of t from transfer function. No, we can get y of t. We have seen also that how we can get y of t for multi input multi output, but we cannot get y of t from transfer function. Now third, I showed you that I am having a CISO system and initial condition is not 0. Then also we can calculate transfer function, but with a condition, that is we assume, that is we assume initial condition is equal to 0. Now talking about yt, can I calculate yt from this transfer function? No, we cannot calculate yt from this transfer function. So I hope this all points are important for you and you have understood it nicely. If you have not understood, then feel free to comment, um, and feel free to text me, message me, uh, and I will clear your all doubts. Now, after looking all these cases, you will say, then, sir, what is the best approach to find out the output? What is the best approach to find out the output? To find out the output, what is the best approach to find out the output? To find out the output. So I will say you that if you are having a CISO system and you know that initial condition is 0, then you can easily get output. I don't have to teach you it again. We have seen it in our previous lectures. From starting, we are seeing that only. But if you have a CISO system, see condition, if you have a CISO system, you are having a CISO system, but you are not sure about the initial condition. If you are not sure about the initial condition, whether it is 0 or not 0, whether it is 0 or not 0, then what will be your best approach? Then what will be your best approach? Suppose, let's take an example of an integrator. Let's take an example of an integrator. Suppose here we have u of t, y of t. Here we are having r, here we are having c. Now, if we take its transfer function, what we will get? We will get 1 by 1 plus src. See, this transfer function I have calculated assuming initial condition 0. I am assuming it. I don't know what is the exact value of initial condition, whether it is 0 or not. But just for the sake of calculating transfer function, I am assuming that initial condition is 0. Okay. Now, can we calculate ys from here or yt from here by putting us, by bringing us this side? No, we cannot do it because I taught you earlier also. because as we don't know anything about initial condition, we cannot do it. So what is the best approach? The best approach is to find a differential equation of it. The best approach is to find a differential equation of it. That is what we will have. We will have ys src ys is equal to us. Now find a differential equation. Find a differential equation. Very important concept I am giving you. Differential equation. Find a differential equation. So if we will find the differential equation, what we will get? We will get dy by dt. Dy by dt. No, we will get something like this. We will get something like this. We will get yt plus rc dy by dt is equal to ut. This we will get. Now take Laplace transform of it, assuming initial condition. Very important. Take Laplace transform of differential equation, assuming initial condition not equal to 0. So what we will get? We will get it y of s plus here we will get rc s y of s minus initial condition is equal to u of s. So what will be our y of s? Y of s 1 plus src is equal to u of s plus rc, this. So we will get y of s is equal to rc, this, by 1 plus src plus us by 1 plus src. This we will get. So from here we will find output. Now we will take inverse Laplace transform. And we will get our output. So very important concept. What I am telling you, that if you are having CISO, if you are and you know that initial condition is 0, then go for transfer function. You will easily get the output from there. But if you don't but if you have CISO but you don't have information of initial condition, then first take transfer function, calculate transfer function, assuming initial condition to be 0, then take its differential equation, then take Laplace transform of differential equation, assuming initial condition is not 0, and then this is the important part. We are taking into account the initial conditions, then we will find y of s, and then we will find yt. So this is the approach which you should execute if you are not sure of whether the initial conditions are 0 or not. Now see, one important concept more that I want to give you. Very important concept is there. Suppose we have transfer function. Suppose we have transfer function. Okay. Uh, you will say that what is the condition? Suppose we have a zero initial condition. Okay. So we have transfer function. From here we can calculate output easily. Okay, fine. Everything is fine. Now you will say, no, sir. Now we are having initial condition, and in all this, and in this case, till now, system is CISO. System is CISO. System is CISO here. Okay. So system is CISO. We are having transfer function. In first scenario, I told you that initial condition is 0. I have a transfer function. I can calculate output. Now you will say that, sir, initial condition is, let me take it like this. Now you will say that, sir, initial condition is not 0. You will say, sir, initial condition is not 0. System is still CISO. Then I will tell you, then go for differential equation. Then I will tell you that go for differential equation. You have transfer function. You know that initial condition is not 0. You have transfer function by assuming initial condition 0. You have transfer function by assuming initial condition 0. But in reality, initial condition is not 0. So from transfer function, I will go to differential equation. So from transfer function, I will go to differential equation. From transfer function which I calculated by assuming initial condition 0, I am going to differential equation. I am going to differential equation. I am going to differential equation, and then I will assume this initial condition, and I will calculate yt. Here I will assume this initial condition and I will calculate yt. Okay. Now here you will say that now my system has changed. My system has changed from CISO to MO. Now what we can do? Here my system has changed from CISO to MO. Now what can I do? So I will tell you that from differential equation, now you switch to state space analysis. Now you switch to state space analysis. State space analysis. State space analysis. And in previous lectures, we have seen that if we have differential equation, then how we can find state space analysis. If we have differential equation, then how we can find state space analysis. So what is the advantage of state space analysis? Here comes the advantage of state space analysis. Transfer function has a limitation. Transfer function has a limitation that transfer function is not defined for MIMO system. Transfer function is not defined for MIMO system, but state space analysis is defined is defined for MIMO system, where we have seen that from state equation and output equation, even if we were having multiple inputs and multiple outputs, then also we were able to calculate yt. So this is very important point. This is very important. If someone asks you that, see, first important one important point we discussed earlier was transfer function was unique, but state space analysis was not unique. I gave you reason that why it is not unique. Here I am telling you that transfer function is not defined for MIMO system, but state space analysis is defined for MIMO system. So here what we had was, we had CISO system, we had transfer function which we calculated by assuming initial condition 0. Then when initial condition was not 0, we switched to differential equation. Now when the system changed to MIMO, we switched to state space analysis to calculate output. To calculate, not, I will not write here yt, because there are number of outputs. I will write it to calculate output. To calculate output. To calculate output. I hope this is clear to you. Now students, here I want to explain you one point that you must remember that we solved this question where we had the state equation, and I taught you how we can calculate transfer function of it, calculate transfer function of it. So you may say that, sir, if we can calculate a transfer function in this way, then what is the need of calculating a transfer function using this formula? Then what is the need of calculating transfer function from this formula which we learned just now, which we learned just now? Then what is the need of calculating transfer function in by this formula when we have this approach, this easy approach which I taught you, that this is in CCF form? Then just we have to verify it from the option that this is the gain here. We have to take it in reverse direction without any sign change. This and for here for numerator this, and for denominator this we will take in reverse with a sign change. But see friend, this is general form. This is general form when you should apply this. Suppose this is given, okay, this is given. Now I taught you that this is in CCF form. What all form we have learned? CCF, OCF, DCF, JCF. So you appear in the exam, you get this type of questions. What I told you, just first try to identify it in CCF. Second, if not, then identify it in OCF. Try to identify it in OCF. Then go for DCF and then go for JCF. And I told you and I taught you that in this different forms, what will be the form of transfer function that you can easily find it out from the options. Okay, but suppose you are not able to do it. Suppose you are not able to identify it. You forgot what is CCF, you forgot what is OCF, what is DCF, what is JCF, you forgot it. If you have the idea, then it's very good. You are going to solve this question in within a minute. But in case you forgot it, then again you have to solve the question or not ना. ऐसा तो नहीं है कि आप छोड़कर आ जाओगे. Then this is the general method. Then apply this method. If you cannot differentiate this, if you forgot how to differentiate it in this four form, then go for this general method and you will get this transfer function. This method is lengthy, but still you will get the answer. कुछ नहीं तो कुछ तो सही. Now second thing, here the matrix A was in CCF form. Suppose we get matrix something like this. Is it in CCF? Is it is in OCF or DCF or JCF? Suppose we have a state model where the model is not in the form of CCF, OCF, DCF, JCF. Then what you will do? You will say that the model was not in any form, so I didn't solve the transfer function. No, you will go for this method, general method. So general method is used when the state model is not in any canonical form. When the state model is not in any canonical form, go for it. Otherwise, if the state model is in canonical form but you are not able to identify it, then go for it. I hope it is clear and there is no doubt now. Now coming to next type, that is type 6. Here we will see that how we can find whether a system is controllable or not, and observable or not. So in type 5, the previous type, we have seen a number of important things. We have seen a number of concepts, number of short tricks, number of statements. Each statement which I have given is itself a concept. So please go through all in details because that's a favorite area in GATE exam. Now coming to type 6, this is also a favorite area for GATE exam. Here what is the problem is that we have to form different matrices to find whether a system is controllable or not and observable or not. And in solving those matrices, a lot of time is wasted. So here I am going to give you short tricks, and I can say that about um 99% of questions will be solved using that short trick only. Yes, in 1%, if the examiner wants you to calculate the matrices, then that's a separate case. In that case, everyone will not be able to solve it through short trick. In that case, every student will go for the conventional method. But other than that 1%, most of the times you will be able to apply short tricks if you know it very well, if you know how to apply and where to apply. So let's start. Then first coming to some basic definitions. Definitions are not important for you, but still we can look into it. So first one is what is called as what is controllability. So if the state of a system can be transferred to another desired state over given time period by using input, then it is said to be controllable. See, suppose we have a counter, and in that counter, our starting states is 000. Now, if we apply input and then the state changes to 001. Now again we apply input, so the state changes to 010. So the states are getting changed as inputs are applied. So it is a controllable system. That is what it is written. If the state of the system can be transferred to another desired state, by using input. Now suppose we have a SFZ, like this. We have a SFZ like this. This is input, this is output. Here we are having some state variable. So state variables are connected with input. That is, state variables are derived by input. So we will call it as controllable. Controllable. Now suppose we have an SFZ like this. Suppose we have an SFZ like this. Here we have input. Here we have output. Here we have state variable. Here state variables are not connected with inputs. That is, the state variables are not derived by inputs. So we will call it as non-controllable. So this is some basic concept of controllability. Not so much useful for exam, because in exams they mainly ask you the questions. But still you should know it if you are studying this subject. So next is what is observability. If all states of the system can be determined from the knowledge of output of the system at a given time, then it is known as observability. That is, we are observing the states. That is, we are observing the states through output. Then it is known as observability. Now coming to how we can calculate whether the system is controllable or not and observable or not. I will give you two methods, each for controllability and each for observability. Please have a look. So first I am talking about method 1. Method 1, how we can find that whether a system is controllable or not. controllable or not. Suppose we have a matrix. Suppose we have a matrix of order n cross n. Then what will be rank of A? Rank of A, rank of A will be equal to n. I hope this is clear. I hope this is clear. We have a matrix of order n cross n. So its rank will be A. Now we have to form a controllable matrix. Now we have to form a controllable matrix. Controllable matrix is formed like this. B. Suppose B matrix is given to us. B matrix will be given to us. B matrix will be given to us. So B, A, B, A square B, and it will go up to A to the power n minus 1B. Here n is the rank of A. N is the order of A. N is the order of A. Now see, if rank of QC, now see, if rank of QC is equal to rank of A, rank of A is equal to N, then it is said to be controllable. Or we can also write that it means, that is, if determinant of QC, if determinant of QC is not equal to 0, then it is said to be controllable. Then it is said to be controllable. I think this point is clear to you. We are having a matrix A of order n cross n. So its rank will be n. Matrix B will be given to you. Then you have to find form a controllable matrix. It will be in this form: B, AB, A square B up to A to the power n minus 1B, where n is the order of A. Now if rank of QC is equal to rank of A is equal to order n, then it is controllable. And in other words, we can say it that if determinant of QC is not equal to 0, then it is controllable. Otherwise, it is not controllable. Otherwise, that is, if mod of QC is equal to 0, then it is not controllable. Or if rank of QC, if rank of QC is not equal to n, then also it is non-controllable. I think this is simple, and you must be having idea about it also. The main thing, the main short trick which I am going to give is the next one. This all must be having the basic knowledge. Now, coming to next type of or next category of question which may be asked in your exam, and that is how to find whether a system is controllable or observable. See, in this topic, I'm going to solve questions by two methods. The first method is the conventional one, and the second method is the shortcut. By using shortcut, you will be able to solve any question within a minute. So let's see. So first is the definition of controllability. Suppose we have a counter and let output of counter is 000. Now this state changes to 001 when we apply input. Now again this state changes to 010 when we apply input. So here we can see that state of the counter is getting transferred to another desired states on application of inputs. The system is said to be controllable. Now let's take another example. Suppose it is example 1. Let's take another example. Suppose we have an SFZ like this. Here we have input, here we have output, and here we have two state variables. So here we can see that state variables are connected with input. That is state variables are input driven. So such systems are called controllable system. Controllable system. Now suppose we have one example like this. Let's take another SFZ. We have something like this. Here we have input, here we have output, here we have state variables x1 and x2. Now suppose this path is broken. Then see, are the state variables connected with inputs? Are state variables driven by input? No, they are not driven by inputs, and they are not controlled by inputs. So we can say it as we generally use the term uncontrollable. So I will write it that uncontrollable. So now you can see the definition and you will understand it. If the state of the system can be transferred to another desired state over a given time period by using an input, then it is said to be controllable. Otherwise, it is said to be uncontrollable. I hope this is clear. The definitions part is not so important for your exam point of view, but still you should have basic knowledge of it, and mainly for interview. If it is asked, then you can define it. Now coming to the next one, observability. So see, if we are able to observe different states of a system from the knowledge of output, then it is said to be observer. Then the system is said to be observable. That is, if we are able to observe, or if we are able to determine different states of the system from the knowledge of output, then it is said to be observable. If the states of the system can be determined from the knowledge of output, then it is said to be observable. So controllability means controlling states, and observability means observing states. So controllability means controlling states, and observability means observing states. These two things are important in control system for the designer who wants to design a control system, because every designer would love to control its states, and every designer should want to observe the states of the control system. So this was all about the definition part. Now coming to the implementation part. How to find whether a system is controllable or observable. So let's talk about method one, that is the conventional method. That is the conventional method. It is also known as Kalman's method because he was the scientist who gave this method. Now suppose I am first we will discuss case 1, how to determine whether a system is controllable or not. So I will write it as controllability test. Yes. Suppose we have a matrix. Suppose we have a matrix of order n cross n. So what will be rank of a matrix? What will be rank of a matrix? It will be n. Now we have to form a controllable matrix. Now we have to form a controllable matrix which is something like this. B will be given. Suppose matrix B is given to us. Matrix B is given to us. So we will form a controllable matrix B, A B, A square B, dash dash, A to the power n minus 1 B, where n is the order of matrix A. N is the order of matrix A. Now see, if rank of controllable matrix, if rank of controllable matrix is equal to rank of A, is equal to rank of A, is equal to n, then system is said to be controllable. Then system is said to be controllable. In other words, we can also say that is, if determinant of QC, if determinant of QC is not equal to 0, then system is said to be controllable. And if this conditions are not met, then our system will become uncontrollable. That is, if rank of QC is not equal to rank of A is not equal to n, and that is if mod of QC is equal to 0, then our system is said to be uncontrollable. Uncontrollable. Okay, fine. So these are the conditions for system to be controllable. This is our conventional method. A matrix we will given, a B matrix will be given. We have to form controllable matrix, and then we have to solve it, find its a determinant, and you can state that whether it is controllable or not. Okay, fine. Now coming to case 2, that is how to find whether a system is observable or not. So I can write it observability test. Okay. Here also same thing. Suppose A is a matrix of order n cross n, that is rank of A, that is rank of A is equal to n. Then we have to form observable matrix. We have to form observable matrix. It will be something like this: C, CA, CA square dash dash CA to the power n minus 1, where n is the order of A matrix. N is the order of A matrix. Now again, same thing. If rank of observable matrix, if rank of observable matrix is equal to rank of A is equal to n, that is, if determinant of observable matrix is not equal to 0, then we say that our system is observable. And if these conditions are not satisfied, then we can say it that it is not observable. So this method, I think that most of you are familiar with. I'm not going to solve questions on this method. You can practice it on your own. You just have to form these matrices and then solve it, having some basic knowledge of matrices, and you can find its rank, and you can find its rank or you can find its determinant. Don't go for rank, you will get confused. Just simply find determinants. Find determinant of QC matrix or Q naught matrix and see whether it is not 0, and if it is not 0, then it is controllable and observable respectively, and if it is 0, then it is not controllable and not observable respectively. Now coming to the shortcut. This part will be interesting, and using this part, you can solve questions within a minute. And in exam, now first let's see that where all Gilbert test can be applied. So Gilbert test for controllability can be applied for two canonical form. That is, if our matrix A is in Jordan canonical form, or if it is in diagonal canonical form. This all canonical form we have seen in details, so I am not going to brief it again here. So Gilbert test for controllability will be applicable if our A matrix is in Jordan canonical form or diagonal canonical form. See, in exam, most of the questions, almost I think 95% of questions, our A matrix will be in JCF or it will be in DCF if you are asked to find observability or controllability, because the examiner also knows that if it is not in this form, then it is very time consuming to find its solution. Suppose we get any matrix like this, then is it possible for you to form its QC and Q naught and find the result? No, it is not possible. So examiner will also not test your patience by giving this type of matrices, and that too not in JCF or DCF. So you just need to know what is JCF and DCF and how you have to identify it. And then after that, your solution will become very easy. Let's see what it is said. A system is said to be controllable if row of B corresponding to last row of each Jordan block is not 0. I know that you will, by reading the statement, nothing is clear to you. Now I will tell you. See, -3, 0, this. See, this is one Jordan block. I have taught you this all earlier. Just refer that session if you are not comfortable. See, this is Jordan block 1, and I told you that this is Jordan block 2. Now, what it is saying? It is saying that we have two Jordan block. First, I will take Jordan block 1. Then I will refer its last row of each Jordan block. This is the last row of this Jordan block. Then corresponding to this last row, or corresponding to this row, I will refer matrix B. And if here we get a non-zero element, then our system will be controllable. Now, for Jordan block 1, the if we refer last row, and corresponding to this row, if we refer matrix B, then we have element 1, which is not 0. So this is satisfying that my system is controllable for JB1. Now I will also check for JB2. So for JB2, this is our last row. This will be our last row. And then corresponding to this, we will refer matrix B. Here also there is element 1, that it is non-zero. So this is our controllable system. Now let's see another example. See, you can see that this is one Jordan block. See, this is one Jordan block. See, this is one Jordan block. This is one Jordan block. This here 1 1 1 are the repeated roots. Now this is another Jordan block. This is another Jordan block. Jordan block 2. This. Now what we have to do, if we consider JB1, then we have to refer last row of JB1. Last row is this. Then corresponding to this row, we will refer matrix B. Here we have to see that this row is non-zero. This row should be non-zero. Here we have one non-zero element and one zero element, but combining both, this row is not zero, is non-zero. So for JB1, my system is controllable. Now coming to JB2, this is my last row of JB2. Corresponding to this, I will refer matrix B, and for matrix B, this row should be non-zero. That is, if both elements are 0, then this row will become 0. If either of the element is not 0, then this row will become non-zero. So for this also my system is controllable. That is, overall my system is controllable. That is, overall my system is controllable. Overall my system is controllable. So I hope now it is clear to you. Very easy. You can see that how easily we can solve it by just looking at matrices A and B. We can give our answer, and that too of big matrices. Now again come here. We have JB1, and then this is JB2. Then corresponding to this, we will refer this row. This row of matrix B is 0. So my system is uncontrollable. No need to check for another only, because we are getting answer here only. This row is 0. This row is 0. So it is uncontrollable. Now, see, this we were talking about the Jordan canonical form for JCF. Now we will talk about the DCF. So it is simple. If you are able to identify that if a matrix A is in DCF, diagonal canonical form, for it I told you that only we will have diagonal elements. That too, all the poles should be unique and not repeated, and other elements will be 0. If we have a matrix in the form of a DCF, then for it to become controllable, my matrix B, all rows of matrix B should be non-zero. All rows of matrix B should be non-zero. So here we can see that this row is not a zero, this row is not a zero, this row is not a zero, but this row is zero. So this system is uncontrollable. Uncontrollable. Very easy. For DCF, what we have to do is that first we have to identify whether our matrix is DCF or not. And once we are able to find it out, then we just have to see that all rows of B should be not zero. All rows of B should be not zero. Now coming to the Gilbert test for observability, here also same two conditions apply, that matrix A should be in Jordan canonical form or diagonal canonical form. So first we will look into the Jordan canonical form. First going through the, let's see the definition, is said to be observable if column of C corresponding to first row of each Jordan block is not zero. Let's see an example, then it will be clear. See here also we are getting JCF. This is JCF1. This is JCF1. Jordan block 1. This is Jordan block 2. Now in controllability, what we were doing was we were referring last row of JB. But in observability, we will refer first row of JB. We will refer first row of JB. And for first row of JB, we will, and for first row of JB, we will refer matrix C. We will refer matrix C, and for matrix C, all the elements of all the column elements should be non-zero. All the column elements of C should be non-zero. So for JB1, we will refer this here. The first column of matrix C is not zero. So our condition is satisfying. Then for this, for JB2, this is the first row of JB2. See, here I told you, uh, here I told you that for this was our last row of JB2, and here I am telling you that this is the first row of JB2. So in JB2, we have only one element, so it will only become the first row or the last row. So corresponding to this, if we will refer, then this is the column of C, and here we can see that all the elements of column of C are zero. So this is our unobservable. Now see a definition, it will be clear. A system is said to be observable. We will start from here. First row of each Jordan block is said to be observable if columns of C corresponding to first row of each Jordan block is non-zero. So we have JB1, we have JB2. For JB1, we will refer the first row, and corresponding to this first row, we will refer the column of C matrix. And if all elements of the column of C matrix is not zero, then we will get, then our system is observable. Otherwise, if for the first row of a JB Jordan block, if corresponding elements, if corresponding all column elements of matrix C is zero, then it will be our non-observable. Now see, here also we can do same thing. Yes, this, yes. This complete is our Jordan block. This complete is our Jordan block with two other repeated roots. So this is our first row of Jordan block. This is the first row of Jordan block. So corresponding to this first row of Jordan block, we will refer matrix C. Here we can see that all elements of all column elements of matrix C is not zero, so it is observable. So it is observable. Now coming to another question. Yes, let's see here. This is our JB1. This is our JB1 and this is our JB2. So here this is our JB1 and this is our JB2. Now what I told you, we have to refer first row of JB1. This is the first row of JB1 and corresponding to this first row of JB1, we will refer first column of matrix C. It is not zero. It is all the elements of column C are non-zero. So it is observable for JB1. Now referring to JB2, see the first row of JB2 is this third row. Third row is becoming the first row of JB2. So here also we will refer third column. Here also we will refer third column of matrix C, and here we can see that all elements of column C are non-zero. So our answer is observable. Our answer is observable. Our answer is observable. Now coming to the diagonal canonical form for checking the observability. Here also we first have to find out whether our matrix A is in diagonal canonical form or not. And if it is so, then we have to simply check matrix C and we have to find out and we have to see that all column elements of matrix C should be non-zero. All column elements of matrix C should be non-zero. So it will, here you can see that all column elements of matrix C are not zero. So it is our observable state. So this is all about controllability and observability. Here I have, we can recap it. First of all, I told you the definition of controllability. That is, if state variables are controlled by input, then it is said to be controllable system. And then I defined the observability. Here I told you that if we are able to observe all states of the system through output, then it is said to be observable. Then I gave you the method one, that is the conventional method, that is also known as the Kalman's method. Here we have to find QC and here and Q naught, and then we have to find that whether determinant of QC and Q naught is not equal to 0, and if it is so, then the system will be controllable and observable respectively. Then then I discussed the shortcut method for finding controllability and observability, but it has a condition that it is applicable to only JCF and DCF. And I told you that in most questions you will get matrix A in either of these two forms. So you just have to identify it and then follow the shortcut, and you will get the answer within a minute. So for Gilbert test for Jordan canonical form, here we saw that we are having JB1 and JB2. So for controllability, we have to refer the last row of Jordan blocks, and corresponding to that last row, we have to check the rows element of B, and if all rows element of B are non-zero, then um, uh, not all elements, that row of B should be non-zero. That is, if suppose here we are having 1 and here suppose there is another element 0, then also my system will be controllable because all elements of this row are not 0. Okay, so our this row should be non-zero. Now same for observability. No, then coming to diagonal DCF. This is not DCF. Yeah, this is the DCF. Here you have to identify whether matrix A is in DCF or not, and if it is so, then you have to check all the rows element of B, and if all rows of B are non-zero, then our system is observable. Similarly, for observability, it is a controllable. Now, similarly for observability, here we have to check the first row of Jordan block, and corresponding to that first row, we have to check the column elements of matrix C. And if that column is not zero, then our system is observable. Now, coming to DCF for observability, we have to first identify that our matrix A is in DCF or not, and then we have to check matrix C that all column elements, that all columns of matrix C should be non-zero, and so our system will be observable. So friends, this was all about your state space analysis, in which I have given you a lot of concepts, a lot of shortcuts. Please go through it, and if there is any doubt, then you can either comment me, or you can contact me directly through WhatsApp, and you can clear my and you can clear your doubt. So thank you.